Having us. Yeah, so today we're going to talk through some of the applications of fan arrays. So fan arrays versus traditional fan systems. Talk about things to consider when you're selecting and sizing fan arrays. Not only the fan, but also motor too, and how that plays a part in your fan selection, trying to align speeds with the fan and the motor together. We'll talk about some of the EC motor technology that's out there today, and then also how FEI or fan efficiency index relates to fan arrays. First of all, just do a quick, look back in history and the evolution of fans used in air handling applications. So you think back, decades ago, it kind of started with being axial fans with adjustable pitch blades. That migrated into house centrifugal fans, which then might with inlet vane dampers to control the volume going through the fan. That transitioned into on-house centrifugal fans, which then, kind of transitioned into multiple fans in parallel, smaller fans on parallel with the introduction of VFDs. And then now everything's kind of migrating to fan arrays in the market. And there's several reasons for that. One of the big things that you're trying to achieve with fan arrays, the basic intent is to take a large centrifugal fan that's running at relatively low speeds, which requires a belt and pulleys to gear down that motor speed to run at a low RPM that the large centrifugal fan or vane axial fan needs to run at, and divide that amongst smaller fans at faster speeds that align better with motor speeds. So you're using multiple smaller fans in parallel rather than one large fan. And by aligning motor speeds, it's easier to couple a motor to an impeller, a standard motor, I should say. It also gives you redundancy. You've got multiple fans running, so if a motor goes out, the rest of the fans can maintain airflow, and you can size them to ramp up to maintain 100% airflow with one or two fans down, where one large fan with one motor, if that's down, is down. Because you're getting rid of the belts and pulleys and bearings, you have lower maintenance. Especially with 5, 7.5 horsepower motors that are permanently lubricated bearings, you literally have no fan maintenance. The motors are permanently lubricated. You don't have any belts, bearings, or pulleys to take care of. So on direct drive fans, you got much lower maintenance, better serviceability. If a motor goes down, these are motors that one person can physically remove by themselves. You don't need lifting equipment. Lower noise. You're using multiple fans at higher speeds, which one would think would be louder, which it is actually louder, higher sound power coming off a fan array, but because they're smaller fans running faster, it's producing higher frequency sound than what you get off a large centrifugal fan running at a low speed. And that higher frequency sound is easier to attenuate than low frequency sound. Lower vibration, shorter axial length, and obviously operational flexibility as far as turning these things down for variable volume systems. So Greenheck started in fan arrays about 15 years ago with the introduction of our house Plenum array model HPA, which were basically fan cubes that stack together like Legos. And this has been very successful with us. It's very easy to install. The fan cubes just stack up like Legos. You bolt them together and wire them up. It has a sound attenuating housing around it. Like I said, with these multiple fans in parallel running at faster speeds, it creates higher frequency noise that's easy to attenuate. So putting a box around with some attenuation really knocks down the sound. And it's easy to service for all direct drive fans. The modular design, so you can pop them out if you have to change out a motor and pop them back in. The market kind of started with these housed arrays where you've got multiple fans in parallel with some type of housing or box around sound attenuation, but we're kind of seeing a trend going towards the open arrays where you don't have the attenuation or the boxes around them. Two of the big reasons is higher efficiency and lower cost in the open arrays. But one thing you have to keep in mind is there's different performance when you're talking open arrays versus housed arrays because of the way that the fans talk to each other, communicate with each other. In the housed array, you've got this box around it, and you can test them individually. And the test data that you get of one fan, you can just multiply times the amount of fans you're putting in parallel, because this fan doesn't know that this fan is next to it when you have a box around or any type of sound attenuating material around it. So when you test a fan in a box like this, it's very easy to predict what multiple fans in parallel are going to produce. is just n times the quantity of fans. On an open array, when you start getting communication between the fans, depending upon the size of the impeller, the speed of the impeller, and the amount of airflow that you're moving, they start communicating with each other, and that results in a loss of efficiency. And AMCA recommends one wheel diameter between wheels when you put fans in parallel. That's generally a rule of thumb, having one impeller diameter between the wheels to get catalog performance. Today, there is no fan array test standard or certification. All fans are tested. Unhoused centrifugal fans are tested like you see here. This is actually a picture in our lab of us testing a wheel. So Greenheck and all of our competitors, when we say a fan array is AMCA certified, what we're saying is that the wheel is certified by itself, and then we are putting it in parallel with other wheels. And AMCA recommends to have one wheel diameter between those wheels to achieve catalog performance. But once again, that is a rule of thumb. Depending upon the magnitude of the air coming off those wheels, you're going to get different performances. So depending upon the space in the wheels, the size of the wheels, and how fast they're spinning and how much air they're moving, you're going to get different communication between the wheels. And we really wanted to kind of understand that so that we could dial in our fan array performance and get the optimized spacing for any given application, size, and quantity of fans. So we developed a test plan to do some R&D and kind of understand fan array applications and become the experts. I'm going to switch over to a video here for you guys to show you here, just to show you, give you an idea of what it took to do this testing. If you look in the lower right, you'll see a whiteboard with a date on it. We actually started October 11th, 2018. And you can see we're moving fans around, different spacing, we're running at different speeds, and this is on one of our AMCA air chambers. And you can see the fans moving around, and then you can actually see the wheels change to different sizes, different configurations. And you can see actually 3 months later, so from August 11th till January 11th, we basically tied up one of our chambers doing all this testing to determine formulas that we could predict what we call fan communication and fan array applications. So after about 400 tests in 3 months, we were able to develop formulas to optimize fan array application as far as for any given footprint or fan array, any volume and pressure, what is the best quantity of fan or impellers, what size impellers and what speeds do you operate at. Let's just give you an example here of some test data to show you what the impact is on putting wheels in parallel. So if I have a 22-inch impeller that can move 7,000 CFM at 3 inches of static pressure, in this particular design, I need to spin it at 1,635 RPMs, and it's going to require 4.68 brake horsepower. If I put 4 of those impellers in parallel and I have 8 feet between the impellers, I'm going to get 4 times the amount of air. I'm going to spin them at the same speed and basically draw 4 times the amount of power, the same amount of power times 4. Because at 8 feet, those wheels are not talking to each other. There's no communication. It's 8 feet on the center distance of the wheels. If I take those same wheels and I put them 44 inches on center, which is 1 wheel diameter between the 22-inch wheels, you can see we start getting some communication. To maintain that 28,000 CFM at 3 inches, I have to speed up the fans 1.3%, and then the horsepower goes up as the cube to that, so about 4.3% more power. If I put them a half wheel diameter, which I've seen many times out in the field, you can see that they start communicating more. We have more losses, so we have to speed up the fans at 3.3%, and we got another 11% increase in power to achieve the 28,000 CFM at 3 inches of static pressure. Now, in most commercial applications, in air handlers, this may not be a big deal because these are all on VFDs. If they don't hit the pressure, the CFM that they're looking for on the field, these basically just turn up the VFD a little bit, speed up the fans a little bit, draws a little more power, probably not a big deal. But when you're dealing with massive fan arrays consuming a lot of power, a couple points of efficiency makes a big deal. This is a picture of some examples of some of the fanneries that we've done, and really why we did all this R&D. If you notice the dates on the testing that we did was back in 2018, 2019. So it's kind of old news. We've known this for quite a while, but we've been kind of focused on some hyperscale applications here that really want to tune their fanneries to run at the most optimum operating point and the lowest um, energy consumption possible. And basically what we're able to do is take that data and then commercialize it into our selection software. And so if you're familiar with our CAP software, you can go in and look at open fanneries, either OPA or MOA, and put in the volume, pressure, and basically the envelope of fannery you're looking for, and then optimize based on whatever's important for that application, whether it's efficiency, power consumption, maybe cost, initial purchase price, sound. You can kind of slice and dice this several different ways depending upon what's important for your client from a fan array application standpoint. So we've got housed arrays, there's open array and a modular array. So open array works very well for built up systems where there's ability to use a crane to put this in place. Maybe there's a situation where it's a built up air handler and labor is a concern. This particular one can be craned into place and then built around it. Or if it's a retrofit application, this would not work very well because obviously you got to break it down and get it down into a basement or up into maybe a penthouse. That's where more of a modular version of a fan array would work better because all these pieces can be broken down into pieces that can be carried in through doors. From a performance standpoint, between a housed and an open array, this is just kind of an example. I've got a 9-fan array. I'm sorry, 9-fan array here. The picture just isn't the right picture here. It threw me a little bit. 8 foot by 8 foot array, 32,000 CFM at 3 inches static pressure. And to compare these two, the open array is going to be a little bit more efficient because it doesn't have the box that's making that air turn 90 degrees off the wheel. So open arrays will generally always be more efficient than a housed array with sound attenuation on it. But with that sound attenuation, you can see that this is about 10 dBA lower sound than the open array because once again, we're using multiple smaller fans in parallel running faster. That's going to make a lot of sound pressure, but it's high frequency sound that's easy to attenuate, so we can really knock down that sound with attenuation around the impellers. But you take a penalty from an efficiency standpoint. And then as far as relative costs, obviously with the open array, you don't have to pay for the attenuation, so it is less cost as well. So from efficiency and cost perspective, open array is a better value. If it's a sound sensitive application, obviously the housed array would be a better value for those types of applications. And then I mentioned before for retrofits, obviously, if you're getting it down into a basement or have some constraints on where you're putting these things, an 8 foot by 8 foot array is not going to be very practical. It needs to be broken down into pieces. And this is just some pictures of the rendering that I showed you before, showing a panel where the wall can be broken down into pieces, fan modules, and then controls package that could be a turnkey solution basically to replace a double wide fan or a vane axial fan in an air handling application. So the controls features basically operate two ways. Either you can set it up so that the building management system basically just passes information through to each fan module. Each fan module has its own drive. So the building management system, if it's sophisticated enough, can run each fan individually, monitor them, turn fans on and off if you want, or a control system can be set up so that the building management system still thinks it's one fan, and it just says, I need this pressure set point or I need this volume, and then the control sequence will tell the fans to run at a given speed, and if one fan goes down, it would speed the rest of the fans up. So there's two ways that you can set the controls up. Basically, the building management can run all the fans individually or still pretend like it's one fan that's controlling and have the controller do all the logic to run the fan array. Now, when it comes to different motor technologies, whether it's induction motors where you need a VFD or permanent magnet motor or EC motor, I use those terms interchangeably, but one can assume that there's a drive included with that particular motor. There's different ways to wire these things. With induction motors, kind of the old school way is just to have individual VFDs for each induction motor. So you send power and a control signal to each VFD, and then each motor has its own VFD. When it comes to fan arrays, typically what you see in the market is combining all the induction motors onto one larger VFD. So if you have four 10 horsepower motors, rather than using four individual 10 horsepower drives, you're using one drive that's rated for 40 horsepower. And then you're feeding each of those motors, but you have to remember you have to have individual overloading contactors in between the drive and each motor, because that drive does not have the capability to sense that one motor is going out. Needs something else to trip out that motor if it's being if it's failing. So for critical applications, we'll see a lot of secondary drives and some transfer gear, so that if that primary drive fails, it can switch over to the secondary drive. On the permanent magnet motors with the built-in drive, it's a little bit more simple. You just run the power and a signal to each individual motor, and you don't have to worry about the drives and or overloads and contactors between the individual motors like you do with an induction motor and a VFD. So that's a little bit on the fan portion of it. When you're selecting and sizing fan arrays, the other thing you have to consider too is the motor and the speed of the motor and the operating point that you're trying to hit with the fan and the motor. So you think about a belt drive fan, it's pretty straightforward. When you select a belt drive fan, whether it's a utility set or inline fan or even a Plenum fan for that matter, you've got a brake horsepower requirement of a fan, and you've got a given speed for that duty point. And then you basically just make sure that the motor you're selecting is higher, the rating of the motor is higher than the fan, and then you have belts and pulleys to basically gear that speed up or down to match the fan speed. So it's pretty straightforward. On direct drive fan, you don't have the gearing of the belts and pulleys, so you really have to pay attention to motor speeds and design point of the fan and try to align those speeds as best as possible. You can use VFDs to manipulate the speed of the motor for a design point, but there's some things that you have to keep in mind when you do that. So I've got a fan array application here. In this example, I'm just running 4 fans to move 20,000 CFM. Each fan needs to run at 2,507 fan RPMs, and it's going to consume 3.6 horsepower each wheel here. And that speed does not align with a typical induction motor speed. So a 4-pole motor running at 60 hertz is going to run about 1770 RPMs. And a 2-pole motor is going to run at 3,500 RPMs at 60 hertz. Now, we can use a VFD to speed up the 4-pole motor to 2507 RPMs, or we can use a VFD to slow down the 2-pole motor to 2507 RPMs. But there's some things that we have to consider when we're doing that. So on a 4-pole motor, we would have to run at 85 hertz. In the 2-pole motor, we would have to run at 41 hertz. Once again, so we can speed up the 4-pole motor, or we can slow down the 2-pole motor to hit this 2507, which is in between. Notice the motor size. So on the 4-pole, we could use a 5 horsepower. On the 2-pole, if we were to slow it down, we would actually have to use a 7.5 horsepower motor, even though we're only going to require 3.6 horsepower out of that motor. And the reason is when you look at a typical motor curve, the motor rating is at 60 hertz. In this case, I've got a 10 horsepower motor. It's a 2-pole motor, so it's going to produce 10 horsepower at 1770 RPMs or 60 hertz. If I slow down that motor, I'm in the constant torque region of the curve. If I speed up the motor, I'm in the constant horsepower portion of the curve. If you look at horsepower, it's just a function of torque and RPM. So if I'm at a given speed and I slow it down and the torque is constant, the horsepower is going to fall with the speed. So a 10 horsepower motor at 60 hertz, if I slow that down to half speed, or 30 hertz, I'm only going to get 5 horsepower out of it because my torque is constant, my speed is falling. On the flip side, if I speed it up, my torque will fall, but if my torque falls at the same rate that my speed is going up, the horsepower will remain constant. If you look at the equation, that kind of makes sense, right? If my torque is falling by 10%, my speed goes up by 10%, the horsepower would be constant. It's important to remember that all VFD rated motors are capable of going up to 90 hertz before the torque falls faster than the speed. So all VFD rated motors can go up to 90 hertz before you start running into horsepower problems. So the message is basically when you're underspeeding motors, you have to overspeed the motor to create enough torque to hit your horsepower requirements. In this case, that 2-pole motor running at 41 hertz, we have to go up to 7.5 horsepower motor to create enough torque to produce 3.6 brake horsepower at that speed. And it's just a linear duration. And that is going to affect your cost. In this case, using a 7.5 horsepower 2-pole motor to slow down and oversize is going to cost 48% more than the 5 horsepower overspeeding. Now, if we rewind about 5 years, we got a lot of phone calls because we've been doing this for a while, and we get a lot of calls from engineers and mainly facilities guys that see fans running above 60 hertz, and they get kind of nervous about that because the mindset has always been that VFDs are designed to slow motors down, right? You slow down the fan when you don't need as much air out of it. There wasn't a very good understanding that you can actually go beyond 60 hertz. A motor doesn't necessarily care what speed it's running at as long as it's within the limitations of the motor. So this is another thing you have to keep in mind when you're making fan selections, because we can provide a 4-pole motor or 2-pole motor. It's basically up to you on determining on which method is best based on the application. Remember that relative cost in this example is just for the fan itself. Per NEC, all the electrical conductors and everything's got to be sized off our rated horsepower. So in this case, even though we're pulling 3.6 horsepower out of the fan or out of the motor, everything's got to be sized off of 7.5 horsepower nameplate. So there's additional costs from wiring and conductors and disconnects and everything else has to be sized for that total rated horsepower, not necessarily the horsepower requirement of the fan. So my message is that's another lever to pull when you're sizing fan selections, is try to get them as close to 1800 RPMs as possible. So when you're in anybody's selection software basically, and you're looking at different fan array combinations between wheel sizes, wheel quantity, spacing, motor RPM and size, or fan RPM is important too, to try to keep close to 1800 RPMs. Tracy, did you want to pause for questions before we get to the next topic, or just wait till the end?
Yeah, we can wait till the end. And we'll, if we need to, we'll come back. Okay,
sounds good. As far as motor technology in HVAC, there's been quite a bit of new developments over the last 10, 20 years. Everything prior to 20 years ago was all pretty much induction motors, whether it's single phase or 3-phase. And then you started seeing EC technology and some of the fractional horsepower single phase motors. The one up here on the left is kind of what most people think about when you say EC motor, single phase up to 2 horsepower motor. But we're starting to see a lot more 3-phase EC motors up into the 10 horsepower. So, that's kind of the sweet spot for fan array applications. Most of the time, fan arrays are 5, 7.5, 10 horsepower motors. So you've got, the German manufacturers, EBM Paps, Zielabig. This is Ultimax by Regal Beloit, and this is the EC Titanium by ABB. So there's several different, motor technologies from an EC perspective, and 3-phase higher horsepowers. The one that we really like is the ABB EC Titanium. We kind of brand this as our Very Green in the 3-phase motors, but basically it's the frame of a typical induction motor, and it's got kind of a real fancy a rotor, so to speak. Once again, this is a fan guy talking about motors, so I'm going to kind of keep it at very high level. So when you talk about efficiency grades of motor. You've got IE bands, so IE3, IE4, IE5, and what we consider NEMA premium efficient motor. Basically, what you buy in an induction three-phase induction motor today is a IE3 efficiency. And a standard induction motor basically just has a bunch of steel laminates in the rotor, and the magnetic force is inducted onto this in an induction motor. Synchronous reluctance is basically using ferrite magnets in a rotor with these special channels cut into it to channel the magnetic flux going through the rotor. And then they boost that by putting additional ferrite magnets inside of the rotor to boost it to IE5 efficiency. And what that means from an efficiency standpoint is here's the bands, and we'll take a 5 horsepower as an example. So IE3, in order to be considered IE3 or NEMA premium efficient, as we would know, like a Bell or Super E motor, needs to be at least 89.5% efficient at full load. IE4 is 91.4, and then IE5 is 92.8. It's basically a 10% reduction in losses as you go up a band. And this is where the ferrite assisted synchronous reluctance of the ABB EC titanium falls. It falls in IE5 band. So you can see it's much higher than the IE3 efficiency band. And it's also more efficient at turn down. So if you look at this graph here, the gold line represents the Bell Super E. This is a IE3 premium efficient NEMA induction motor at turn down. You can see as you turn it down from 100% load, the efficiency starts to fall. The gray dotted line here you see is one of the external rotor motors that you see in fan array applications, and then the gray line is this EC titanium motor. So you can see not only is it more efficient at full load, which you see here, but as you turn it down, you can see that delta separates even more. And fan arrays are never running at 100% load of the motor, right? They're always somewhere in between. So as you turn down a motor, the efficiency starts to drop, where this type of EC motor really kind of is a lot flatter than what you would see in an induction motor or an IE4 EC type or EC motor. So basically, just to wrap this up, different types of fan array applications, whether it's housed fan array or an open array. And then when you get into open arrays, you've got, one piece designs versus modulars that are easier for retrofit applications, and then different types of motor technology and control sequences that would go with each of those. In Greenheck's case, on both the housed and the open, we can do either induction motor or a EC motor, and then the modulars are all EC motors just because they're a little bit lighter weight than the induction motors. Any questions on fan arrays?
Okay, yeah, we have a couple questions that have come in. Anybody who wants to add in there, you're more than welcome to. First one is
Tracy, real quick, I
Yeah.
do have a section on FEI. I figured I'd get through the fan array and motor questions first. And if we have time, I can hit on the FEI and how it applies to fan arrays, but I didn't want to run out of time.
Yeah, that's good. Is it a safe assumption that the horsepower comparison between one large fan and 6 fan array will be pretty much the same? Or are there instances where the design could have a situation you might have a single 100 horsepower versus a 6 with horsepower less than 100?
Good question. There's not a yes or no question or answer to that. So it depends on the application. So you think of like a large double wide centrifugal fan. That's a pretty efficient fan as far as you've got a wheel and you've got a scroll on the wheel, and the scroll sometimes adds 10 to 15% efficiency to a wheel. You take that away, you start losing efficiency. But on those large fans, you have to do a belt drive because of the speeds. So you've got the belt and pulley losses and the bearing losses that hold that shaft up, in addition to the motor losses. So there's a trade-off going from a large fan to smaller fans. From an efficiency standpoint, I've seen it both ways depending upon the application. Relatively speaking, though, it's pretty much like for like efficiency. I'm not going to tell you that a fan array will beat a large centrifugal fan from an efficiency standpoint every time.
Yeah. How do the differences in performance based on fan separation and housing type change the static pressure? As the static pressure drops, do the changes in efficiency sound increase, decrease, remain the same?
It's all relative. So for given configuration, fan spacing, size, as you go down that system curve and the static go down the curve, the sound and the power consumption are relative.
Yeah. Are there any other options besides BDD to control airflow back through the failed fan?
That's a great question. So there's basically three options. So one is a backdraft damper, which is nice because it's automatic. So, the backdraft dampers are designed so that when a fan's on, it opens up, right? And if a fan fails, it shuts automatically. The drawback to that is cost, because you have to buy a damper for every fan module, right? You just can't buy one. And then there is some pressure drop across that damper. Some manufacturers say that there isn't, but there is. And the second option is a blank off panel, which is basically just a cake pan that would fit in the inlet of the fan. The nice thing about that is it's relatively cheap because it's just a piece of sheet metal. There's no performance loss. The drawback is it's manual. Somebody's got to put it in. But some customers we've dealt with, they've got, think like a big hospital, they've got maintenance staff, they're 24/7, and their thought is if a fan goes down, I've got a guy that's going to go look at it anyways and verify it. He can throw the cake pan in there, and they might have a motor on the shelf somewhere that he can have it swapped out in a couple hours anyways, back up and running. Third option is do nothing at all. We've got some customers that will just have motors on standby, and if a fan goes down, they can literally swap out that motor in an hour or two and have it back up and running. So they're not so concerned about actually, shutting the fan down or stopping the flow back through it. Now, we would always recommend shutting the whole array down when you're doing stuff like that, but that's our recommendation. It's not necessarily what happens in the field all the time.
Is that like fan monitoring system come built in? How are you picking that up?
Yeah, so we've got the Sure Air system monitors flow going through the fans. Um, our current state is not sophisticated enough to identify fans going down, so we do it through current monitoring, but that's something that is in the works right now.
Mm-hmm. Okay. What is the optimum number of fans for fan array for flow efficiency?
That's another good question. I would say, generally speaking, for typical applications, if you're talking like 30 to 60,000 CFM, it's generally, I would say, like 7 to 10,000 CFM per fan is kind of the optimum. So you're generally talking 4 to 8 fans depending upon the application. But we've seen applications where they're moving 100,000 CFM, so it's hard to say, but generally 4 to 8 fans is kind of the sweet spot when you take a look at, all the volume of all the sales that we do.
Yeah.
It seems to be a sweet spot.
Okay. Yeah. If you want to look at FEI real quick and go over some things on there, it's definitely an important topic. I know that's coming. So.
Okay. So basically, efficiency as we look at today, typically you're talking static efficiency or total efficiency if it's a ducted application. And basically what that is shaft power into the fan. So when you look at a system, when you look at a fan system, you're really talking about electrical power into the drive, the VFD or the motor, and then air power out. And for, the entire life of the HVAC industry, we've always talked about static efficiency, and that's really fan shaft power. It always ignored belt drive losses, VFD motor losses, and basically it's just shaft power through the fan. FEI is a wire to air metric. So it's measuring electrical power in and fan power out. So it's really more of a true measure of the fan system power. And, today with today's motor technologies and VFDs, that's really what you want to understand is the full efficiency of the system, not just the aerodynamic efficiency of the fan. So FEI is basically a simple ratio of a reference electrical maximum power divided by your actual power. And so basically, if you're above 1.0, you're selecting and applying a fan below the maximum electrical power that you should be inputting into that fan. And if you really want to understand the math, there's 4 standards that you can buy from AMCA and read through 222 pages to really understand the math. But the good thing is they created a certification program to put on the fan manufacturers to do all the math for you. And as long as you see that label that it's got FEI certification, you can trust that we did the math for you and it's all certified. So what does that mean for a fan selection? So let's look at like 10,000 CFM at 3 inches of static pressure. The baseline electrical input power would be 7.96. And I use brake horsepower just because we're in the US. It's actually calculating kilowatts, but basically the baseline power is 7.96 electrical power in. Now, it doesn't matter if we're talking an inline fan, utility set, plenum fan, fan array, and axial fan, any type of fan. To hit an FEI of 1.0, you have to select and install the fan below an input power of 7.96 to be an FEI of 1.0 or greater. So let's just look at a utility set at that duty point. So you can see the baseline power is the same no matter what fan size I use. And these are all utility sets, just different fan size. Now, as I go up in fan size, I'm going higher up on the fan curve, right? So I'm consuming less power as I go to a larger fan size. And the FEI goes up as the fan power goes down, and then basically where my fan power intersects the baseline power is where I'm at 1.0. Now, the cool thing about FEI is just a ratio, right? So I can look at this and say, okay, 1.16. If I have a fan that's 1.16, I know that's exactly 16% more efficient than a 1.0. So it's just a simple ratio when you're comparing fans. Once again, this applies to all fan manufacturers, all types of fans. So it's just a simple ratio. And what it's basically doing is when you look at a fan curve, typically, your high efficiency is 2/3 the way up the fan curve for any given fan. And down here, it's very low efficiency, and then you get into a surge type area. And this FEI baseline is basically creating bubbles that are compliant for selections and kind of the more efficient part of the fan curve. And what this does from a fan product perspective, if you have a low efficiency fan like a box inline fan where you just have a centrifugal wheel inside of a box, this is a relatively cheap fan, but it's also not a very efficient fan compared to a mixed flow fan that's got a very efficient impeller, a stator section, and a tube, right? So what it does is basically going to create smaller bubbles for less efficient fans. You can still use these fans, but the operating area where you can actually select it and be compliant with FEI is going to be smaller than that of a more efficient fan, just because the efficiencies are much broader on a more efficient fan. So Asher 90.1 had this back in 2016. We haven't seen a lot of traction. People calling us asking about this based on energy standards. Where we're getting a lot of questions is all the rebates that are out there right now. So this Seattle City and Light, the entire West Coast right now has rebates through the power companies for FEI targets. In this case, 1.25, 1.4. You can see the different types of fans and power consumptions. Minnesota has it through Xcel Energy, and we're seeing this basically migrate across the US. And, you see we have FEI published in our selection software and certified through AMCA. This is a utility set. We also have that through fan arrays. Important thing to understand though when it comes to fan arrays though, is you have to think of this as a system, right? So when FEI is calculated, and I don't want to get too much into details here, but you look at fans, motors, wire to air, and there's bigger tolerances for smaller fans because motor efficiencies are lower as you get into smaller motors. So the tolerance on a 5 horsepower is going to be higher than a 20 horsepower as far as efficiency goes. So you got to look at this as comparing, if I've got a 50 horsepower fan array, because I've got 5, let's say 60 horsepower, 6 10 horsepower motors, 5 wouldn't make sense. I'm comparing that to a 60 horsepower fan, not 6 individual 10 horsepower motors. And that's how you have to calculate FEI. But I'm getting a little bit too far into the details. Just look for the FEI certification. You'll be good. Questions?
All right, so we do have one more question that came in. This is back on fan arrays, I think. But what is the impact to motor life when running them over 60 hertz?
Good question. It depends on the manufacturer. There's basically 2 things that can go on a motor, right? The mechanical, which is the bearings, and the electrical, which is basically the windings, insulation on the windings. And like I said, from a VFD rated motors need to go up to 90 horsepower 90 hertz in order to be VFD rated. That means that they're usually class F insulation. So the windings are covered to go up to the temperature rise that you see on 90 hertz. And then it comes down to the motor manufacturer and the bearing life on the motors. And I can't tell you that specifically. I do know, just because we worked with Baldor on the Super E's, that all those the bearing life is rated at the max. It is on the 4 poles. They use the same bearings as the 2-pole motor, so they're already rated for 3,600 RPM. So that you're not degrading the bearing life at those higher speeds.
Yeah, good.